Hello students, in this today's session we are going to study about the design of two-way slab which is prestressed. In structural design and drawing 3 we are going to design the two-way slab by prestressing techniques. So let's start the design procedure of two-way prestressed slab. So what is mean by two-way slab? So when the rectangular slab is supported on all the sides and the length to breadth ratio is less than 2, it is considered to be a two-way slab. Means this classification of slab is depending upon the two basic criteria. One is the support condition of the slab and second, length to breadth ratio. The slab spans in both orthogonal direction. A circular slab is also a two-way slab. In general, a slab which is not falling in the category of one-way slab is considered to be the two-way slab. Okay. Now, in case of two-way slabs, if we have rectangular two-way slab, this we can divide further into following types like flat plates. So in structural design 2 we studied that how to design a slab, how to design a RCC slab, means how to find out the reinforcement of it and how to find out the depth. But here in structural design and drawing 3 we are going to design this two-way slab by prestressing techniques, not by RCC. So for RCC we referred IS 456 and here for prestressing we are going to use both IS 456 as well as IS 1343. So the first type of two-way slab by using prestressed techniques we can call it as the flat plates. So these slabs do not have beams between the columns. The drop panels or the column capitals were also absent in these flat plates. Usually these are the splendial beams at the edges. Means if we compare the flat plate with the regular RCC slab, it doesn't have any beams. Also it doesn't have the column caps or the column capitals or drop panels. It only usually have the spandrel beams at the edges. Second is the flat slabs. So first is the flat plates, now we have the flat slabs. So these slabs do not have the beams but have the drop panels or the column capitals, means nearer to the top of the column or at the junction of column and slab. We have certain projected area that we are going to call as the drop panels or the column capitals. In the next slide it will be more clear to you how that flat plates and flat slabs looks. Third type is the two-way slab with the beams. There are beams between the columns if the beams are wide and shallow. If the beams are wide and shallow, they are treated as the band beams. Means means these two-way slabs will consisting of the beams. Actually beams is the load carrying member or the load transferring member from slab to the column. In first two cases the load of slab is directly transferred to the column, whereas in two-way slab with beams the load of slab is transferred to the beams and beams will transfer that load safely to the columns. Now for long span construction there are the ribs in both spanning directions of the slab means for the larger span, uh, where we are not going to provide any beams over there. So in that cases, we have in both in orthogonal direction we have the rib-like structures, and that type of slabs which has the ribs in both orthogonal direction is called as the waffle slabs, and that ribs we are going to term it as the waffles. Now, the two-way slabs are also present as mat or raft foundation. Yes, in case of mat foundation or the raft foundation, we are going to provide the reinforcement in both the direction. So that mat or the raft foundation is also the representative of the two-way slab. So here, through the pictorial presentation, we are going to understand what is the meaning of the flat slab and flat plate and flat slab. So as we discussed in the previous slide definition, so see here, in the flat plates, uh, 1, 2 and 3, 4 columns are there, and in between these columns we don't have any beam. We are not going to see any beam over here, and around the periphery of this column, we haven't seen any projection part. Means we have only the flat plate resting on the columns, and these arrows represent the reinforcement or the tendons we are putting in both directions. So this we are going to call as the flat plate, where beams were absent and column capital is also absent. Now in figure B we have the flat slab. In flat slab, yes, there is no beams, but around the periphery we don't have any beams, but around the periphery of the column we have the extra projected part to take the load of the slab plate. So this extra projected part we are going to call as the column capital, and this entire structure represented as flat slab. Now in figure C we have two-way slab with beams. Yes, in structural design 2 we design the two-way slab of this method. Okay, so we are familiar with this. We put the reinforcement in both the directions, and the load of this particular slab is going to take by the beams supporting to that slab, and it will transfer that load to the column safely. So this is the two-way slab with beams, and this is what the waffle slab. So see here, here we have the ribs in horizontal and vertical direction. We prefer the waffle slab where the spans between the two columns is more. Okay, so this is for the pictorial representation of the types of slab, types of two-way slabs. Now in case of two-way slab, the absence of beams in flat plates and flat slabs leads to the following advantages. So the absence, yes, definitely, yes, the addition or the subtraction or the removal of any particular part of the structure, it has its own advantages and disadvantages also. So first of all, we are going to see what are the advantages of the flat plates and flat slabs where beams were absent. So the very first advantage of two-way slab with no beams or the absence of beams is the formwork is simple. Yes, of course the formwork is simple because whatever projection we need to do, so that work is removed. So see here, we can understand this through the help of diagram. So if I have a slab with beam, then I need to provide the extra box. We need to provide the extra box for this projected part or the beam. So instead of that, if I provide, if I remove this part, beam part, then I need to provide just flat plate to support the slab, and in this way it will save my time, as well as it is simple. Means to do this kind of arrangement, some extra efforts is required, whereas here in the case of flat plates or the flat slab, I need to provide just a horizontal platform, so it makes the form work simpler. Okay, now the second advantage is reduced obstruction to the service conduits. Yes, in case of buildings, residential buildings or the commercial buildings, we need to provide the water supply connections, we need to provide the electricity supply connections. In that cases, if we provide the beams, it will take more effort, it will require the more efforts as compared to the flat plates and flat slab. Why? Because we can see the example with the same drawing, we can see that example. Suppose we need to provide the water supply line. So if we have the beam, then we need to provide the number of joints. In this case, means at this corner we need to provide the joint, in this corner 1, 2, 3 and 4 more number of joints we need to consider, means this extra efforts we need to require. Whereas if I have the horizontal platform, then I will put just single conduit to carry that water or the electric lines. So that's why it will reduce the obstruction to the service conduits. Right. The third application of this two-way slab. So this two-way slab is more, it provides more flexibility in the interior layout and refurbishment. So as there are less number of obstructions, as there are less number of obstructions in case of flat slab, there is no projections at all. It will give us the plane surface, and that plane surface will provide the more flexibility for the interior layout, because if we have the projections in the layout, we cannot use that area effectively. So that is what the application of this flat plate or flat slabs. So here we can see the example for the flat plates. So as per the definition what we discuss is there is no beams. If we see here, we cannot see any beams. Also at the top of this column we don't have any projection portion too. Means this is a single plate which is directly resting on the columns, and that's why we are going to call it as the flat plates. Here we have the flat slab. In flat slab, as we discussed, there is no beams, but nearer to the column or the top of the column we have the projected portion over here. We can see in this photograph this projected portion. In this slide we can see that the projected portion. See here, this is the photograph of flat plate. As we discussed from the definition of the flat plate is the type of slab where beams were absent. So from this picture it is clear that we haven't seen any beams over here, and at the top of this column or at the junction between the slab and column there is no extra projection provided. Means here only the flat plate of slab is resting on the column. So this type of slabs we are going to call as the flat plates. Now here we have the flat slab. The difference between the flat plate and flat slab is, in both the cases there is no beam, but in case of flat slab we have the extra projection at the junction between the column and slab. So this projection we are going to call as the column cap. Okay. So this we can see from the figure. So see here, I am going to highlight that portion. So this projection is present in flat slabs. So this we are going to call as the column capital. Okay, so this is what the basic difference between the flat plate and slabs. Beams were absent in both, but in flat slabs we have this extra projection. So this is nothing the column cap. So this projection is provided to transfer the load of the slab safely to the column. Okay. Now the analysis. So before going to design anything, the prior step is to analyze that particular structure. The analysis of two-way slab is given in the section 31 of IS 456-2000 under the flat slabs. The analysis is applicable to the flat plates, flat slabs and two-way slabs with deflecting beams. For two-way slabs with beams, if the beams are sufficiently stiff, the method that is based on the moment coefficient is given in the annexure D of IS 456-2000 is applicable. Now we are going to see the design step of two-way prestressed slab. So the very first step to design the two-way prestressed slab is identify the type. So the identification of the type of slab is based on two criteria. One is the support condition and second is Ly by Lx ratio. So here if the Ly by Lx ratio means longer side divided by shorter side ratio is less than 2, then we are going to call it as the two-way slab. Step 2 is the thickness of slab. We are going to identify the thickness of two-way prestressed slab, and for this we are going to use the empirical formula, that is span divided by 50. So here we are going to take the span in meters so that we get the thickness in meters, or when we take the span in mm, then we'll get the thickness in mm. So step 2, thickness of slab, we are going to calculate it by empirical formula span divided by 50. So once we get the depth of that particular slab or the thickness of that particular slab, in step 3 we are going to calculate the loads, because we require this load for the analysis. So how we are going to calculate the loads? So in load calculations, we are going to calculate the total service load, which is nothing but the addition of self weight of slab, live load acting on the slab, and floor finishes if we have. We calculate the self weight of the slab by using the formula B into H into density of concrete. So remember that here B we are going to consider as 1 meter for the slab, H is nothing but the thickness of slab, and density of concrete we are going to use as 24. Live load, many times the numericals which is asked in university exam or any exam, the live load value is directly given. If it is not given, then we need to take it from the IS code, but many times it is given. The value of floor finishes we are going to take it as 0.12 kN per meter square. So for the self weight, we are going to add floor finishes and self weight, means self weight and floor finishes all together we are going to call it as the dead load, and live load value we are going to consider from the IS code. So this is what the step 3 of two-way slab, prestressed two-way slab design. Ultimate design, see, if we are following the limit state method, then we need to find out the value of design ultimate load by multiplying the total service load by partial safety factor. So for RCC, now we are going to use that partial safety factor as 1.5. So the IS 1343 2012 from table 7, we are going to take that values. Now the step 4 is working moments in the middle strip. Now this is what the analysis part. So the analysis of two-way slab, we are going to uh, find out the moments, working moments by using the table 26 of IS 456 2000. So here we can see the diagram. So as we know that we are doing the calculations of the analysis for the two-way slab, and in two-way slab, in both orthogonal direction, in x direction as well as in y direction, we are going to provide the strands or tendon. So we do the analysis one by one. So first of all, we are going to find out the moments for span Lx. So this is the diagram for span Lx given in the IS 456 2000 annexure D of page number 90. So see here. So Lx is the smaller side and Ly is the longer side. So we are calculating the moment along the span Lx. So this moment takes place in this direction. See here. So this Lx span is going to bend in this fashion. So moment along the span Lx. Okay. So for this Lx span, we are going to divide the span into two parts. One is the middle strip and another is the edge strip. So the middle strip length for span Lx, we are going to take it as 3/4 of Ly, and for edge strip we are going to use that value as Ly by L8. So do remember that for span Lx, we are taking the middle strip length as 3/4 of Ly, right? So how we get that working moment? So the moment formula is also given in the IS code. So that formula is mx is equal to alpha x w into Lx square. So this value of coefficient alpha x we are going to calculate by using or by referring the IS code. Now this is what the moment, unit moment, but we want to calculate this moment for the total middle strip, because when we are going to calculate this unit moment, so here what we consider is the unit width of slab, but we want to provide the strands or tendon in the entire middle strip. Okay, so for entire middle strip, if you want to find out the total moment, we need to multiply this unit moment by the total span of the middle strip. So the total moment in the middle strip is nothing but total span of the middle strip into the unit moment, that will give us the total moment in the middle strip. Okay, so while doing the calculations or while calculating the eccentricity and the effective depth, we are going to assume the cover in the x direction as 30 mm. Okay, so these assumptions we need to do while calculating the working moments for the middle strip. Next step is calculating the total pre-stressing force. So in step 4 we calculated the moment, total moment, and by using this total moment we are going to find out the value of force. We know the relation between the force and moment. What is that relation? Moment is nothing but the force into perpendicular distance or force into the lever arm. So here if we take the cross section of the beam or the slab, here we are going to consider the slab as the beam of unit width, that is 1 meter width. Okay, so from that basic expression, we can calculate the force as, see here, force is what, we know the basic relation, M is nothing but M is equal to P into Z, where Z is nothing but the lever arm. So P, prestressing force, we can calculate as, if we are going to take this lever arm on this side, so multiplication becomes division. So total moment divided by distance between the top curve and the center of the cable. So this is nothing but the lever arm for this. So we know that the total moment is mx into span of the middle strip for Lx plus the distance between the top curve and the centroid. So this is nothing but curve zone plus eccentricity. So this is nothing but the curve zone plus eccentricity. For this we used the stress diagram. We already discussed the stress diagram. So from stress diagram, suppose in the bottom zone, if we provide the tendons with eccentricity E, and as this is what the final stage stress diagram, or the service stage, we can say service stage stress diagram. So at bottom we have the zero stresses, and at top we have the maximum stresses. So the resultant value of compression, is in the zone above the neutral axis. So this is what the neutral axis, and this position, the resultant compression position, is nothing but the K top. So the lever arm becomes, so the lever arm is nothing but the distance between resultant compression and resultant tension. So that lever arm is nothing but the addition of Kt plus E. And we know that for rectangular section, this Kt is nothing but h by 6. So h by 6 plus E is nothing but the total lever arm distance. So this is what the total lever arm distance, E plus h by 6. So by using this formula, we get the value of prestressing force in x direction. So this is what the step 5. Now to calculate the moment, because whatever formula we have, that includes the moment coefficient. So that moment coefficient values for Lx and Ly direction, that is shorter span coefficient and longer span coefficient values, is given in the table 26 of IS 456 2000. So that alpha x and alpha y values depends upon the support condition. So here I have taken one simple example. If the 4 edges, means suppose if I take the intermediate span of continuous slab, then it becomes a case of 4 edges discontinuous, and the positive moment will take place at the middle. And to get that magnitude of positive moment, we are going to use this table. So the case is 9. Now Ly by Lx, yes, we can calculate this with the help of given data. And for this Ly by Lx value, we have the values of alpha x. So these are nothing but the alpha x values. Suppose the Ly by Lx ratio is 1 by 2. Suppose the Ly by Lx value is 1 by 2. Then the alpha x is 0.072. And for that particular value of Ly by Lx, so alpha y has a common value for the case of 4 edges discontinuous, and that value is 0.056. In this way we get the value of alpha x and alpha y. And once we get the alpha x and alpha y, we can calculate the moment in x direction as well as in y direction. Okay, so this table is very important. We are going to refer this table while calculating the moments. Step 6 is calculation of number of strands and its spacing in the x direction. See, in the previous steps we have calculated the moment. By using moment we have calculated the prestressing force. But each strand or the cable has certain limitations, means it is going to take the load up to certain limit. So to take that maximum, means whatever value of P we have calculated in step 5, sometimes it is much more greater, and to take that greater value of P we require the number of strands. So how we calculate that number of strands? In x direction or y direction. So here in x direction, how we are going to calculate number of strands? So the total pre-stressing force means capital P value divided by force in single strand. Now this value of force in single strand is given in the numerical, or we can get the value of single strand from IS 6006. Okay. So from IS 6006 we can get the value of force in a single strand. Okay, so this is the step number 6. Now once we get the number of strands, we need to decide the position of it, where we are going to place it, or what is the spacing, is how we are going to place that number of tendons. So the calculation of spacing of the strands we are going to find out as total middle strip length divided by number of strips. Suppose this is what the width, and this width is suppose 10 meter, middle strip width is 10 meter, and if we have 5 numbers of strands, so the total strip length is 10 meter, number of strands 5, so 10 divided by 5 means 2 meter, means at every 2 meter distance we are going to provide the strands. Every 2 meter distance we are going to provide the strands. So this is what step number 6, number of calculation of number of strands and the spacing of it in a particular strip of the slab. Now we'll go for the next step. Now here again I have written the step 4, because why I have written step 4? Because it's a repetition. Initially we have calculated the moment, prestressing force and number of strands of cable in x direction. So the next step is we need to repeat the same step for y direction. So that's why step 4 is working moment calculation in the middle strip in y direction. So what is the formula? Formula is given in the IS code, annexure page number 90. So see here. Now what we are going to consider? We are going to consider the span as Ly. So for Ly span, how the movement takes place? The movement is going to take place in this fashion. And for Ly span, what is the middle strip length? Middle strip length for Ly is 3/4 of Lx. So see here. So for particular span, the middle strip length is vice versa, opposite of that. So that we need to remember. And this diagram is there in the IS code, page number 90. So we can directly refer this figure. Okay. So the formula is My is equal to alpha y W into Lx square. So this Lx square is the common term. We already used this formula for two-way slab design in SD2 RCC two-way slab, but here we are designing the two-way prestressed slab, but the basic theory is same in the both cases. So Ly, so in every moment equation we have the Lx square only. For y also we are considering the minimum span. And once we get that unit moment, we need to calculate the total moment. Total moment, how we are going to calculate? Just multiplying it by middle strip length. Here we assume the cover as 40 mm. So in x direction we assume the cover as 30 mm, but here we assume the cover as 40 mm. The reason behind that is very simple, because we are going to provide the strands in both the directions. So this is what x direction, this is what y direction. So if we provide the strand in x direction with cover 30 mm, so if we provide If you provide that strands of the cable in y direction, they are not at the same level. It is going to overlap. So to take care of that overlap length, we provided the more cover to the cable, that is 40 mm. Then question may arise is why not we are considering the less than of 30? So 30 mm is the maximum limit. We cannot go beyond that. So minimum 30 mm cover is required for prestressing. So we cannot go less than that. So that's why initially we provided 30 mm and then we provided the 40 mm cover. Now calculation of prestressing force, yes, we use the basic formula over here. Moment is equal to force into lever arm, moment in y direction. Lever arm value is not going to change, h by 6 plus e, and in this way we get the moment in y direction, prestressing force in y direction. And after getting the value of total prestressing force, we are going to calculate the number of strands and the spacing of that strands. Okay, so this is the repetition in x and y direction. So that's why I have kept the common numbers, say 4, 5, 6. Now the up to step number 6, our design is done. Now whatever design we did, we have to check that for certain checks. So step number 3 is the first check for our design, and that check is the check for limit state of collapse. So in this check, what we are going to do is we are going to compare the moments. So what moments we have? We know the loading condition on the beam slab. Okay, we know the loading condition on the slab, and by using that loading condition, we can calculate the moment mu. What is that moment? If that loading condition, if that load is in the form of UDL, okay, and the beam is simply supported, then ultimate load is WS square by 8. Ultimate load, moment is what? Ultimate load into W, means W is nothing but the ultimate load, Lx square divided by 8. In this way we get the moment, actual moment, and the ultimate moment of resistance. Ultimate moment of resistance is given in the annexure D of IS 1343/2012, page number 51. And according to that clause, the moment of resistance, ultimate moment of resistance is MUR is equal to FPV APS into bracket D minus 0.42XU. So see here, this value of prestressing force, this is nothing but the value of stress developed in prestressed steel. Okay, so this value of stress we can calculate with the help of table number 11 of IS 1343/2012, page number 51. So I have included that table 11 in the next slides. So we get this value of FPV by using table 11. So one of the column of the table 11 is represents APS, FPU, BD into FU. Okay. So we are using this term. So for that, initially first of all we need to calculate the value of FPB by 0.87 pu, and from this we get the value of FPB. Okay, so it will be more clear when we are going to see that table 11. So what is that check? If the ultimate moment of resistance in x direction is greater than ultimate moment in C, if the moment of resistance is greater than the actual moment takes place, then the structure is safe. MUR means resisting moment must be greater than the actual moment takes place. So this is what the check for limit state of collapse. Okay, then this is again the same slide is repeated over here. So here we are going to check that for x direction and y direction, ultimate moment in x direction and ultimate moment in y direction. Okay, now next is the step number 8, check for the deflection under service. So deflection check, many times we are not going to use this deflection check for the slabs, because in last year for ST2 two-way slab we haven't used check, but in the projects, uh, mini projects given in the term work, we need to apply this check for the deflection. So for the calculation of this deflection check, or to check this deflection, first of all we need to calculate the balance load. We know the calculation of stresses. So calculation of stresses in the beams. Three methods we used here before. Stress method we use for the calculation of stress, then load balancing method and force method. So by using that load balancing method, we first of all we are going to calculate the balancing load. Now we are going to compare that balancing load with external load. That will give us the residual load, and we calculate the moment for this residual load. And by using that, we are going to calculate the deflection. That deflection formula is given by the Sir Timoshenko in his theory. So according to him, the formula for that means deflection coefficient, first of all we need to calculate. So alpha max is nothing but the deflection coefficient or the design deflection. So alpha max is equal to alpha into bracket q lx raised to 4 divided by d. So where alpha is nothing but the coefficient over here, coefficient given by the Timoshenko, and that coefficient depends upon the value of Ly by Lx. So here for the Ly by Lx 1.5, the value of alpha is 0.0072. So depending upon that, we have the different values of alpha. So here small q represent the residual load. Small q is nothing but the residual load. Lx is the span in x direction, and capital D. Now step number 9 is the check for stresses. This is the last check we have. In this check we are going to calculate the maximum compressive stresses, and we are going to compare these total compressive stresses with the allowable compressive stress. So first of all we are going to calculate the moment due to the residual load in x direction. Already we have that moment value. So by using that moment, we are going to calculate the stresses developed in x direction by formula m by z. So this m by z formula is derived from the basic bending theory which we studied. So this we can study. So m by z formula, this stress we can find out with the help of basic bending theory. We know that m by I is equal to stress by y. So this is the bending equation. So when we take this y on this side, we get the stress as m into y divided by I, and this I by y is nothing but the section modulus z. And in this way we get the stresses developed by the moment due to residual load as m residual divided by section modulus. At the same time we are going to calculate the direct stresses developed by the prestressing force as P divided by A, and this P divided by A plus this moment due to this stress due to the residual moment gives us the total compressive stresses. And this total compressive stress value we are going to compare with permissible compressive stress in bending, that is sigma CBC value, which is given in the IS 456-2000 table 21 of page number 18. In this way we are going to check our design for the stresses.